So this week we're going to make a little bit of a transition. We're going from last week, which was, think of your quiz. It was all descriptive. So we talked about mean, median, mode, standard deviation. We talked about range, and we described variables, characteristics one by one. In inferential statistics, this is the break, right? So this is the break where we cover something different. So again, past sessions, descriptive approach, describing, the average age, the level of education, gender, those kind of things. Now we're going to actually move into statistical testing. So this is like the real deal of where we're going. And this is why level of measurement is so important. So we're going to test either samples to a larger population, or with hypothesis testing, we could test a sample to a population, or we can compare groups, group to group. So we're going to learn things like what's the null, what's the alternate, which we talked about. Hypotheses can be one or two tailed. They can, we need to test for significance, right? In the culture, we say, oh, that's really significant. But the thing is, we don't know unless we test it statistically using statistical tests to see what that p-value is. And we're going to talk about that. And then we'll talk about type 1 and 2 errors as we go through. So again, in the past, we were learning about testing. Now we're going to test. So I put this slide together because I want you to understand that, again, statistical testing uses quantitative data, and we want to make sure that the results that we find are not by chance. Again, think of inferential statistics, taking a random sample from a population, doing some testing, and then referring or generalizing back to the population. These are all quantitative approaches. This is all ways of looking at results that occur by not by chance, right? That they're meaningful and they're real. So we want to make sure, again, that these results are real. And we want to make sure that it's not a mistaken calculation. It's a bad way that we've pulled the sample, maybe a bad way we've defined a hypothesis. So we have these procedures that we're going to talk about. And the biggest thing you're going to look at is this p-value, right? So you can have a relationship that has a large statistic, a coefficient, a number, but unless you have the p-value that is appropriate, and I'll show you that in a second, you can't say that there's any relationship that exists between the variables. The p-value is the ticket to tell you about significance. So what do, right? This is a silly example in a way, but it's just to get you thinking and have something relatable, right? So the null hypothesis is a statement of nothing, right? I know a lot of people think, well, that's kind of weird. Why would you begin by stating nothing? But the null hypothesis is not the hypothesis that you're looking for. It just says that there's no result and there's no difference or statistical difference between the sample and the population. So the null hypothesis, it's all about rejecting or failing to reject the null. And you want to reject the null always so that you have the other hypothesis, your alternate is true, right? So this is the example. We're looking at comparing grades of our class, of course, our class, right? We're el más mejor, right? We're the best, to all other undergrad classes. So you can say in the null hypothesis, you would state it in words that there's no statistically significant difference between the mean or average score in our class versus the university mean, right? So what you're doing here is you're testing the average of a smaller group compared to the average of a population. This is what we're looking for. Again, the alternate is where you state the relationship that you're seeking to find as a researcher. This is where you're stating what you're really, really looking for. And you're looking for a difference, right? If you're going to do a hypothesis test or look at a sample and population, you want to see how different they are, right? So that's where this alternate hypothesis comes in. This is what you're predicting. So you could say, and there are many ways you could talk about alternate. Alternate can be have several forms, right? It can be one-tailed or two-tailed. It can have no direction. So you're saying, as an alternate, there is a statistically significant difference between the average grade in our class and the university. But we often, when we do research, we just don't care. We care more that there's more than just a difference. We want to predict a direction of the difference. So usually your HA, or your alternate hypothesis, will predict the difference. So you would say that you would predict that that the average grade in our class is statistically significantly higher, right? That's the direction than the university average. Or you could say lower, but you see the difference? Saying there's a difference, it could be higher or lower. When you predict a difference, you're predicting a direction, right? That something is lower, less than, greater, more than. And this is the difference, right? If you're looking at just difference, and I'll show you a depiction of this in a second. If you're looking at difference, it's a two-tailed test. So you don't care if the difference is higher or lower. When you're looking at a one-tailed test, you're looking to see if the mean is greater than or lower than. So this might help, right? When you are looking at a two-tailed test, these are the regions here, right? Do you see this region? Both of these regions, if your score falls in this region, you can reject the null and find a result, right? Accept the alternative hypothesis and reject the null, right? So you don't care where your scores fall. As long as they fall here, you can say there's a difference. But if you say that it's a one-tailed test, either that the scores are greater than or less than, you only have a lesser region to find a value. So here, if a value falls in here or here, you can say, yes, I reject the null, and there is a statistically significant difference. Here, if your values fall in here for your test, you can say, yes, there is a statistically significant difference, and the scores of the sample or the class are greater than the scores of the university. Here, if your score falls in here, what you can do is say, yes, in this one-tailed test, we can reject the null and say that the scores of our class are lower than the average in the university. So this is a visual depiction, but right now I just want you to grasp this concept that if you say your alternative hypothesis is just finding a difference, it's a two-tailed test. You have two regions to reject. That's it, right? To reject. If you say it's a one-tailed test, upper tail, you're predicting greater than. One-tailed test, lower than. Lower tail, it's less than. So ponder that a bit, right? What do we hope for? We hope that we reject that null. We state the null, which is no difference, but we want to find difference, right? That's why we're doing research in the first place. So we always want to go to reject that null. Reporting results that say there's no statistically significant difference between the sample and the population are not super meaningful, right? Think back to the paper about septic shock, right? They found no statistically significant relationship. So what do we do with that? How does that help us in research? How does that help us in our practice? Right? This is the thing we really, really care about. And often researchers will say, yeah, you did the test or whatever you did, but what's your p-value? And we tend to look at it, and if you think of the way we rate everything now within our culture, the higher the amount of asterisks, the higher the level of significance, right? So more asterisks, right, these symbols, the better the significance and the less by chance. So if you think about this is the level that we set as like the baseline. We say that if your p-value is less than or equal to 0.05, what it means that there's only 5% chance that you got the result by making a mistake. And you can see that the percentage of making a mistake gets lower and lower as your p-value gets lower, right? So what you want to do is really make sure that the smaller the p-value, the tinier the p-value, the more likely it is that the results you're finding are based on statistical testing and not based on chance or some, or error or something, right? So the lower the p-value, the better. And I'll show you in a second in a table from an article. So this is our goal standard, right? We look at a p-value and we'll accept it. So we say, look, this means that 5 times out of 100, we're okay saying that we said something was statistically significant when it wasn't. So making 5 mistakes out of 100 is okay. Is it better if we make, 1 mistake out of 1,000, right? If we go up in the p-value levels, yeah, right. So the 1 in 100, or if we make 1 in 1,000, it's better. So we want to decrease the amount of times we're making mistakes in what we're doing. So we want to keep that p-value very, very low. And if you see, who works, right? What's going on here? Normally we would have asterisks around these numbers, but you see a p of 0.47 has no statistical significance. So you might have a test that reports a very high coefficient, like a chi-square or t-test. But when you look at significance, it's not significant. Therefore, you cannot report that relationship. You can report it and say it's not significant, but you can't report it as a meaningful finding. Here, like this p-value is awesome, right? If you see this when you're doing research, you'd probably fall on the floor and not believe it because it's so low. But it means that that the relationship you're finding here is at the highest level of significance, right? We could 3-star this, right? And that what you're finding is based on the science and the math and the testing. It's not based on chance, right? So lower p-value, better. The minimum p-value we accept is 0.5. When I came up in research, we used to accept marginal p-values. If people were really, pushing it, we would accept a marginal p-value of a 0.1. So we'd say 10 times in 100, you can make a mistake, but marginal p-values are not really helpful. So this p-value is what you're looking for, right? This is very, very low. I would give this 3 asterisks. This, sorry, but not significant. So now take a look here. All right, let's look at this table a little bit. And it's looking at which groups have aggression. Right? They're using chi-square. Chi-square we'll talk about later. It's just a test that looks for association. No biggie, right? No direction, just association. So what matters, right? They're looking at sex and they're looking at prevalence of aggression. They find no difference. P-value is not significant. We're looking at race, right? They're reifying or conceptualizing race. No difference in aggression. They're looking at caregiver education level. Look at this. This value is 3 asterisks, right? At the level of 3, which is incredible. All right, let me see if I can annotate. I'm going to try to. Okay. So this one is at the level of 3 asterisks, right? Again, look here. This one as well. This is less than 0.001. This is significant, right? This is not. Let's look for the last significance. This one is. So if we had to make some discussion about this, we could say that, many variables were tested to look at this association, and the only variables or variables that were related to aggression were caregiver education level, right? Self-injury and GI problems. So the other variables, although they might be quite interesting, we might think they're important, they don't pan out. The only ones that pan out are these. Oh, sorry. I don't know. I'm a little bit obsessed now with, sorry, with adding features here, sorry. All right, so think about that. Oh, let me get rid of these guys. Sorry. Oh, let me get rid of them. 1 second, I gotta unannotate. Let me just clean the, there we go. Okay, sorry. Yeah, annotations are fun, but sometimes they're not super fun. So in the next session, we'll talk about some of the common statistical tests. Chi-square just tests for relationship, association, no causality. T-tests are really great. We're fortunate that t-tests let us do a lot of different things. And we'll talk about them in the next class, but I want you to think about independent t-tests. Here, we'd look at like cases and controls, right? 2 different groups. So are the cases and controls in your study different, right? And then paired t-tests look at groups in a population. So if you do pre and post testing among 2 groups, do they differ? So different ways of looking at statistical testing. Just to bring this up now, we'll definitely go over it more in the next slide set. And we have to be able to interpret, right? Looking at a table, seeing statistical significance, it's all well and good, but if we can't express it, what does it mean, right? If we can't write it in an article or write it in a paper, it's really meaningless. So for example, we looked at GI problems and aggression, and the interpretation would be there was a statistically significant difference between children with and without GI problems and aggression, right? And then if it was a randomized control trial, we would say there's a statistically significant difference between the control and treatment group in terms of anxiety. So in the first example, you're comparing 2 variables together. You're comparing GI problems and aggression, right? Those 2 things. When you're doing a randomized randomized clinical trial, what you're doing is you're looking at statistical differences between your treatment and control group, right? So 2 variables in one set, and then in the other set, you're looking at differences between groups. And this will become clear the more we talk and use this kind of language. So I'm gonna take a break. We'll go back. We'll hop back into some common statistical tests, and then we'll go forward.